that it's possible to be aware of a scene in the absence of an agent. Okay, so I'm going to make that point very quickly. The second point I'm going to make has to do with the utility or perhaps absence of utility in the case of fMRI and other such techniques. It's a very mixed bag, but it's really the behavior that a lot of people, particularly coma scientists, have used to get at the problem of defining what a conscious human being is in the case of a pathology. So as a matter of fact, people like Adrian Owen in Canada, Stephen Lorius in Belgium, and Nico Schiff at New York Hospital, I believe, have delved into this to some extent. And in fact, in the case of Adrian Owen, they've used fMRI as a very valuable tool, not necessarily to see what's happening when you're aware, but as a metric for a yes-no question, for example. So they happen to take a history of a patient. The patient was once a tennis player before he had a traumatic brain injury. He's been rendered in a persistently vegetative state, and in fact, they can't get any answers out of him, but the doctor says, okay, I want you to imagine you're playing tennis and you successfully hit the ball over the net, and knowing from other people, healthy people and patients as well, that when that happens, some area of premotor cortex and cortex lights up in a very particular way, can be used as a metric for a yes versus a no answer. So they say, well, if you want to answer yes to the questions I'm going to ask you, imagine yourself lobbing a ball over the net. And in fact, they've achieved some convincing data that suggests a lot of people that seem to be in a deep coma state, in fact, have some sense of some degree of awareness. Okay, so now I'm going to talk a little bit about what I do. And I'm going to need your help, Neil, to get me on the screen really quickly. So I'm Lightning Edelman. Yeah, I think it's free form is better. That's better. Okay. Good, that's great. So I'm not going to talk about who I am, my background, more about what I do. So octopus is my model organism. I am intrigued by octopus mainly because I was interested in the problem of consciousness starting in about 2005 after many discussions with Bernard Bars, who is the original author of global workspace theory many, many years ago, back in the 80s. And we wondered what it was to be aware if you're an animal. And I wondered about the periphery of this. What are the boundaries, the evolutionary boundaries of this? How far can we go? Is it possible to be aware if you're an invertebrate? So octopus naturally came to mind. And the other reason that I was intrigued by octopus is that they're this profoundly elegant evolutionary experiment. They represent a life form that has this complex nervous system that is far and above more sophisticated than any other invertebrate. It's rather remarkable. They compete. They have 500 million neurons, if you're talking about a common octopus, 200 million between the eyes. That's twice as many as a garden variety laboratory rat. Laboratory rats are no slouches, believe me. And the other 300 million neurons in the arms. This is rather remarkable. So that really got me thinking. The other thing that really interests me is the eye of the octopus. Yes, lightning talk. So I'm going to get along really quickly, and I'm going to go right to this movie. So what we've done is we've tried to set about figuring out what certain cognitive benchmarks we can study in the octopus, akin to the same kind of cognitive benchmarks that have been studied in the vertebrates. So you're going to see an example. I hope I can just play it, and I'm going to talk over it. If you can kill the sound on this, that would be great. So kill that sound. So this is an example. This is an animal that's negotiating a Barnes maze, and it's doing it in a terrestrial fashion. It's out of the water. And so in effect, Barnes maze demonstrates cognitive maps in the vertebrates. That is, the animal can navigate. The animal has some sort of spatial sense of space and can navigate to particular objects of interest or to an escape. In the case of the octopus, this is a negatively aversive situation. He wants to get out of the light and he wants to get back into his water. So he's highly motivated to find his escape hole. There's only one true escape hole, everything else is fake. If you notice, right above the true escape hole, there's a plus sign. Very quickly, the octopus learns the location of that plus sign and it will go to that plus sign. Even if you move that plus sign to somewhere that isn't the real hole, that is what happens. So that's pretty striking. So we're going about setting these benchmarks up, and you know, we're really interested in how the octopus thinks. I'm going to ask two questions and I'm going to end it here in relation to the idea of an interspecies internet. So what kind of communication media or device can be devised to bridge the gap between octopus and human representational transforms? This is very tough. They're not embodied like any vertebrate. They're very unusual. The second question, how can we accommodate the uniquely embedded aspects of cephalopod sensory and motor features in devices that we design and implement? Again, very complex because the animal both has a central brain, a central nervous system, and a peripheral distributed nervous system, and that's reflected in the arms. So it represents a very serious issue. So finally, what I believe can come out of this are a series of universals about what it is to be an animal that is aware functionally and even structurally, because the octopus represents this beautifully elegant cul-de-sac of evolution. It does not look at all like a vertebrate, and yet it has complexity that rivals the vertebrate. And I'll end it there. Sorry, it was not so lightning.
Okay, whoever's next.
I'm Chris Braun, and I'm Braun here, that second one. Braun, I can see if that works. So I would like to tell you not about any work I do on consciousness, but about what I think to be the oldest known distributed electronic communication system, and that is the system of communication and sensing used by weakly electric fishes. There are two groups of weakly electric fishes, one in Africa and one group in South America. That's the group that I study. And you can see here from these very lightning talk style slides with everything in 5 slides in one. This is a electric fish called Hypopygus that lives in the margins of the Amazon River Basin. And like the other 100 so species that it's related to, they have a set of cells in their tail, it's most of their body in fact, that generate weak electric fields. And those are summed up to create a field that will surround its entire body. They can sense that field and use that to communicate with other fish who can also create a field, or to image their world. And there's 2 basic types. One that uses a sort of sinusoidal pattern of voltage changes, shown on the right column here, and then one that's more pulsatile on the left. And I'll give you, hopefully, some examples. Let's see. So here's what we call the tone fish. That's enough of that. And then there's the pulse fish, which is the ones that I study. And they create these, in that case, very constant repetitive pattern where each discharge sounds to us like a click. So they can use this to hear each other, to sense each other, or also to sense the world. So they use this like sonar or echolocation in that the field surrounding them is distorted by other objects that differ from the water. And so if there's a conductive object on the upper right there, the field lines will converge. Or if there's a resistive object, the field lines will diverge, and they can sense that in the changed pattern across their body. The problem is they also sense the fields of other animals. So when there are 2 animals next to each other, say as shown in that little cartoon on the lower left, they jam. And there has been a lot of work by neurophysiologists and neurobiologists to understand how these animals attempt to avoid this jamming interference to maintain a good sense of electrolocation. And we study these pulse fish here in the cartoon, where you can just imagine you have one fish that's 50 hertz, the other is 51 hertz, and they can either increase the difference or try to match and lock on at different times. And I'll just skip real quickly. I won't tell you anything about that, but I'll tell you how we eavesdrop on them in the wild. So we can use these little simple audio amplifiers and a stick and poke around, find the fish, it's really easy fishing, and know what species is there and what they're doing in their home. So I'll just play a couple quick examples before I leave you. Here's one species that is rather irregular at rest, but you will hear it get excited. It's a longer clip than I hoped. We know something about that animal's mind right now. Some are a little more dramatic. That's an animal looking around. That's an animal interested in the stick we just poked into it. So I'll leave with that and just say this is a distributed electronic communication system that lets us know something about their mind from a distance with rather simple technology.
Thank you. Don't quit it. So my name's David Rothenberg. I play music with animals. And they could be birds, they could be whales, they could be bugs. Let's just play it. Here. This is my latest project, is about making music with nightingales in Berlin. And but I think the whole thing began maybe almost 20 years ago when I was playing in the National Aviary with a white-crested laughing thrush. Can turn it up a little. Because music really is a form of knowledge. It's a way of learning about the world. And so in this process of playing with a musician with whom I cannot speak, you know, it's just one step further than what Peter was talking about earlier. When you're doing world music, you're always playing with people with whom you cannot talk to. We don't share a spoken language, but music somehow connects people. We can make something that makes sense. And you can expand this idea to go to other creatures like this laughing thrush. Who knew until you walked around this place with a clarinet that this bird might be able to make music with us? Okay, so now many years later, I've gone off to Berlin to play with nightingales in the wild. This city is full of nightingales, and it's also a city full of interesting musicians, and we go out there in the parks in the middle of the night and see what can happen. Here I am with the Turkish electronic musician Korhan Erel. He's playing an iPad. He's kind of mixing and matching and sampling these birds and playing their songs back to the bird. So pretty soon you can't tell what is the electronic bird, what is the actual bird. And in many years that we've done this, you know, you really start to understand the aesthetic of what the species is doing. This is something Darwin wrote about. Why, he said, birds have a natural aesthetic sense. That's why they've evolved beautiful feathers and beautiful songs. And to understand that sense, you can play along with it. Some of this work leads to scientific papers with some of the people we've talked about here, trying to turn musicality into something that can be quantified the way that, you know, other things are quantified. This also is happening at Hunter College. I think next time I'm going to play with these electric fish. It really sounds like a good idea. So we've made a film that just came out about this process, Nightingales in Berlin. You can see it's really interesting to bring different kinds of musicians out to do this for the first time. Okay, well, I can stop there. And what this is about is how, you know, music can be made from one species to another, and that, you know, when you get different kinds of people, they're changed by this process. And the more time you do this, you can start to share in the aesthetic sense of many different species by doing this, thinking about it, sometimes analyzing it, sometimes just playing. And I think really more and more people should be doing this. And it's surprising how little attention there is to the music of animals, from which our own music certainly evolved. You know, there's a handful of people doing this work around the world. There should be hundreds, there should be thousands. So thanks a lot.
Hi everyone. Well, so Lightning talk. Let's say that you want to learn a new language, and imagine, if you will, that to do so you cannot see or even interact with other people, but you can only hear. So let's try to decode the following audio. Now let's try again, but with visual input.
Deixa. Pega os canões.
Now it's easier, isn't it? So we can see that one of the characters is talking and the other one is leaving a gun. So maybe the shawarma means leave the gun. And then he takes a package. So maybe Pecos cannoli means take the cannoli. So that's why in the Race and Maniasco lab, we are working with video information to decode dolphin behavior. We are using deep neural networks to identify, track, segment, and encode the position of dolphins in aquaria and in the wild. And together with high-resolution sound spectrograms, we'll be able to know who is saying what and in which behavioral context to decode dolphin communication. Thank you. 1 minute.
Well done.
Can I actually put this on there? I don't need the computer. Can I turn this on? Okay. Hi. No PowerPoint. Sorry, I had no idea I would want to say something when I was. Okay, good. And I'll try to be quick. So I'm a philosopher of mind, and I've been interested in the hard problem of consciousness. And I thought something should be said about the hard problem and its relevance to the field of comparative animal cognition studies. But Philip Wall actually summarized things very eloquently. So I won't say anything about that, but I want to say still, not something about the state of the art about the problem of the hard problem of consciousness, but how animal studies actually could shed light and help the hard problem. Before that, just a quick footnote. Neil asked whether it is the case that nobody knows about. Nobody knows anything about consciousness. I would actually like to say that that's not true. Compared to the periods in which the problem of consciousness overwhelmed a lot of otherwise very smart and reasonable people over the last 250 years, and if you look at the history of science vis-a-vis consciousness, it's very instructive to see how there have been periods of crisis regarding the problem of consciousness. We know a huge amount. However, we are going through another period of being overwhelmed about consciousness, and there are several interesting, both intellectual and sociology of science-related reasons for it that I would get into, but it's not true that nobody knows about anything about consciousness. So one problem with the problem of consciousness is that consciousness means a whole lot of things, and a few times the word consciousness was uttered in this very conference today. It was sometimes meant social consciousness, sometimes self-consciousness, and so forth. And these are all different, related but different issues. So one way to talk about the problem of what's called the hard problem of consciousness is perhaps to talk about sentience, or something like felt experience. That's what David Chalmers meant originally anyway. How is it that in a biological organism, out of a physical process in an embodied being emerges felt experience. A very simple form of felt experience is pain. So one can ask the question, do all biological beings who show pain-like behavior in fact feel pain? Or do some of them just have appropriate behavior without the experience itself? So that is actually a central problem, a central question in the literature in the hard problem of consciousness. One can look for structural reasons why a certain organism has, or it would make sense to think that it has felt experience of pain, whether it has a nociceptive system in its anatomy, for example. Or you can look at behavioral data, and that, I think, goes a long way. Although I think that a more central argument needs to be made in terms of the functional role that felt experience has. Why is it that certain organisms have felt experience over and above pain-like behavior and appropriate anatomy? Does that provide any reason, does that provide any advantage in evolutionary terms for the organism that has the felt experience? Now, that involves thinking about the minds of animals in a more integrated fashion, because I think it makes sense to talk about or ask questions about felt experience. I am, okay, ending, sorry. In relation to the affective system and the cognitive system of the appropriate animal. So I just want to say that the various amounts of data that come from comparative animal studies actually help dilute the mystery that surrounds what's called as the hard problem of consciousness. It's one thing for a question to be deep, which I think the problem of consciousness is a deep question, and it's another thing for it to be a mystery. The more we realize that human beings are in the midst of all other animals and not on top of them or at a chasm away from them, the more it's easier to think of sentience in a graded continuum, and therefore ask problems about the hard problem of consciousness in a richer and more varied framework. So, thanks very much.